Alright, for this lesson, the only example we're going to look at is dealing with an underdamped oscillation. So the idea here is when we've introduced a damping coefficient, what we've actually done here is we've taken our normal amplitude or maximum displacement from equilibrium and we've added to this exponentially decaying term here. And what you've been asked to find is if I provided you with the damping coefficient, right, so that's this lambda d here, you might want to figure out how much time it takes for the amplitude to reduce to 1/3 of its original value. Now, how you do this is taking a look at your function here. All you're concerned about is the amplitude. So if you take a look at the amplitude, it's always whatever's outside the sine function. So our current amplitude, so we'll just call this d current, is equal to our initial amplitude, or this initial d equilibrium maximum, multiplied by this exponential term. 1 second here. I just need to get a lambda symbol here. Times the time. All right, so our goal is to deal with this. Now, what we're doing here is we're looking for how long it takes for this to reduce to 1/3 of its original value. So what we want to do here is basically we want to take each one of these equations and we want to divide each one by d initial. And the reason for this is we're told that the current amplitude divided by the initial amplitude needs to give us 1/3. So this here gives us 1/3 on this left-hand side here. And on the right-hand side, we are simply left with the exponential term here. Now, you can do a bunch of things to this. One thing that I might recommend you do is this 1/3 here is kind of annoying. We can actually replace it with a decimal if you like. But at the end of the day, you need to solve this particular equation. And a lot of people struggle with solving this because for some of you, this is something you've never seen before. Our goal is to get t by itself here. To do so, we need to get rid of everything that accompanies t on the right-hand side here. Now, this e here is actually the exponential function. On your calculator, for most of you, or at least if your calculator sucks like mine does, this is actually written as an exponential function. So it uses the exp button in some calculators. Now, the reason why old school calculators do this is this exponential function here is actually a trigonometric style function like sine and cosine were. Just like sine and cosine, it has its opposite function. And that opposite function is the logarithm function, or the natural logarithm function. If you apply this natural logarithm function to both sides, like so, 1 second, it does much the same thing that sine and inverse sine do. In other words, on the right-hand side here, it is an inverse function that actually removes the exponential function. Right? It simply just gets rid of it. And so you'll be left with the logarithm on the left-hand side here is equal to negative lambda times time. Now, with that being said, we can actually use this very, very quickly to find the time that we need to have here. The reason we can do this is the logarithm function, so the logarithm of 0.333 or 1/3, whatever you want to use, actually gives you a number. Right? The logarithm of 0.333 gives you a literal number of negative 1.0996 or something like that. On this side, we have a negative sign, and we know that lambda is 3 hertz. And our goal is to find t. You can do this very, very quickly using some algebra. And you'll find that t is equal to 0.367 seconds. And so that's how many seconds it'll take for the amplitude to reduce to 1/3 its original value. Now, the reason I bring this up is because some people were not quite sure in previous years how to go from this step to this step. And you do so by simply applying the natural logarithm function to each side. Right? And that's all you need to do to deal with this. So you will be asked in this course to deal with a variety of these exponential type functions. So you really, really need to know how to solve for something that's inside the exponential function, or to the power of base e. And the trick is the logarithm gets rid of it just like sine and cosine do. Right? And that's it for this example, and that's it for this week.